Yeah.
Are you one of them?
All right. So we introduced second order equations, and we'll eventually be able to solve any linear second order differential equation where these coefficients P of t and Q of t, and then the right-hand side may be any functions of t. But for now, we're going to keep things simpler and just look at everything that's multiplying the x's and the dx and dx squared, d2x, all the derivative of x and x's are multiplied by constants. So these a, b, c are constants. And then we're only looking at homogeneous. And then we'll do in non-homogeneous. Probably we get to it today. So if you try to solve this, you can't do something like we used to do when we had first order. First order, you could have done separation. But we could kind of do what we've been doing with other problems. Well, with like non-homogeneous problems, we've always looked at the equation and proposed a solution form that we think would be reasonable. And in this case, if we said c e to the rt, that's going to be fine because then the derivative of an exponential is an exponential. And so you'll have a bunch of exponential terms, and what you want to do is try to get the c and the r so that it'll end up forcing this thing to satisfy this differential equation, which results in the same as satisfying the characteristic equation or solving the characteristic equation. And you have three cases. So you have the case one is where you have distinct real roots. We looked at that, and then we also showed that you can have two homogeneous solutions because you have a second order equation, and the sum of both of the homogeneous solutions will also be the solution to the differential equation. So the general homogeneous solution is built off of adding two homogeneous solutions together that you get. And there's always going to be two because it's a second order equation. And we then also did an initial value problem that requires having two conditions for two unknowns. So we ended with this case where you have a repeated root. So if you have a characteristic equation that gives you a repeated root, we can tell that one of the solutions for sure will be the e to the 3t, because that's r is equal to 3. The other one, it would be redundant to just say e to the 3t as well. But you can have the e to the 3t, but it'll be multiplied by t. And this is something I'll have to show using reduction of order later. But for now, we're just going to use that. And in this problem, we also have two initial conditions. We have one condition on the function. We have another condition on the derivative. So it's the same process that we've been doing before. You'll just apply the initial conditions. So the first initial condition is just saying that x of 0 x of 0 is equal to 2. What does that mean? That means that you plug in, this is the solution, so you plug in 2 into the x, and then you plug in 0 into all the t's. So this e raised to 0 is 1. This term just goes away. So we're done with the, for this condition gives us the c1 is equal to 2. Let's do the other condition, which is the derivative condition. This requires us to compute the derivative. So I'll just say that maybe we can just use the derivative of this is going to be x prime of x prime of t is equal to 3c1 e to the 3t because of the chain rule, plus there's a c2 that I'll leave out and then do the product rule. So it'll be t's derivative is 1 times you copy the second, plus you copy the first times the derivative of the second. That's the derivative. And then you need to apply the condition. So it says that you have x prime at 0 is equal to 25 over 3. So that just means that you're going to have 25 over 3 is equal to 3 times C1, which is coming from the fact that the e raised to the 0, because all the t's are going to have zeros in it, plus this t times 3e to the t will go away, so you just have this term, so it's just going to be C2. And then e raised to the 0 is 1. And we know that C1 is 2 from what we just computed here. So you can get that this is just the same as 25 over 3 equals 6 plus C2. And then C2 would just equal 25 over 3 minus the 6 is the same as 18 over 3, just so that I can get this to be 25 minus 8 is 18 is 7 over 3. So this is our C2. And we're done. So we just plug those into the C1 and C2 in our general solution. So we have this thing right here, but then I'll just say that our C1 happened to become 2 after we plug in this initial condition, and C2 ended up being 7 over 3. That's just an initial value problem. Again, you need 2 conditions for 2 arbitrary constants, C1 and C2. But the point in this repeated roots case was that we needed to include this t in the second homogeneous solution. Okay, so that's repeated roots. Of course, you remember from your algebra class that there's 3 cases. And it's really from the quadratic formula. There's something called the discriminant, which is inside the square root of your quadratic formula. And if that's positive, then you get 2 distinct real roots. If that's equal to 0, you get repeated roots. And if you have a discriminant that's negative, you have complex roots. So if you were to look at this one and try to find the characteristic equation and solve for this one, you'll end up getting, so let's write the characteristic equation. The idea is that x double prime will become r squared plus the 9x will become what in the characteristic equation? Yeah. It'll just be 9. Yeah, exactly. It skips the x prime term. So maybe I'll write it and say the x prime term would have been, like if there was x double prime, x prime, that would have been, but in this case, it's 0. So there's really no r term. It's just the 9 term. And this is equal to 0. Of course, that's just the same as r squared plus 9 is equal to 0. And you can factor this and get r, well, I won't factor it. I'll just say r squared is equal to negative 9. And then you can just take the square root of both sides. And r will equal plus or minus 3i. So you have a negative inside the square root, and so you'll have this plus or minus 3i. This is a complex root. So the same theory works from before. You could say that the solution is going to equal 2 homogeneous solutions. So there is 2 because there's 2 roots here. And you say one of them will be c e to the positive 3it. And the other one will be c2 e to the negative 3it. And technically, this is correct. It's in complex exponential form. But it's common for most applications to look at trying to find just the real solution. So how can I convert this to just looking at what are the general real solutions? You got to get these complex exponentials to become, written in a form that allows us to make this real, or at least get a hand on what all the real solutions would be. And you may have seen this, but there's a formula that allows you to take a complex exponential and split it into its real and imaginary parts. And that's called Euler's formula. And the Euler's formula says e to the I theta is equal to the real part is cosine of theta plus I sine of theta. So this allows you to split into the real and imaginary parts. Let's do that to each of these two complex exponentials. So there's one here, and there's clearly another one here. Well, they're slightly different. So let's do the complex exponential for the orange one, which is going to be just the e to the 3it. Here, I'll just write it this way so that it's consistent with this. It's I theta, so I'll just say I times 3t. Right, so 3it is the same as I times 3t. But then this allows us to tell what the theta is for this. This is like our theta. So this is written as I theta. If we write it in the same form, then 3t is like our theta. And so when you use this formula to extract the real and imaginary parts, this will become cosine of 3t plus I sine of 3t. And so we've taken this and successfully written it in trig form, where the real and imaginary parts are separated. Now you have the other one, which is this kind of the same one, but it will be in negative up here, negative. And I'll put I, well, maybe I'll just do it this way. So I'll just keep it I, and then this time it's multiplied by negative 3t. So for this one, our theta is negative 3t in our Euler's formula. Yes.
Could you put the negative sign in front of the
E
plus I sign?
Yeah, you could do that too. I would, yeah, so you'll see the same thing will happen. So you'll have this is now cosine. Well, I guess, yeah, well, it'll work because this is an even function. So this is 3t, negative 3t, because our theta is negative 3t, plus I sine of negative 3t. And I think what you were saying is that eventually this should be just the same as cosine of 3t minus I sine of 3t. And it will be because cosine is an even function. So an even function makes this just like you can just drop the minus sign inside the even function here. And then sine is an odd function. So you could take the minus off here, but then you have to subtract. So this is the property of sine and cosine is that they're even and odd functions. So you could rewrite this in this form right here. And so this complex exponential is the same as this. So that's the property of even and odd functions. It says that you can do this. It's basically saying that if you have cosine evaluated at some value that's negative, so to the left of the y-axis, it will be the same value as that same negative number made positive, just because it's got y-axis symmetry. And the sine is has origin symmetry. So if you're like evaluating at at negative pi, it will be the same number as in pi, but like it would have been flipped above the x-axis. So we've now used Euler's formula, and then this used even and odd properties of cosine and sine to write this each of these two complex exponentials into trig form, where you have split it into its imaginary, real and imaginary parts. So let's just use these versions of, so that does that give us? So our x of t is equal to C1 times parentheses all of this. This was our orange complex exponential, plus you have C2 times the purple exponential was this. So I'll just copy and paste that. So you have these two. And I'll even further just say, okay, so this one is our orange one, and this one is our purple one. And now I'm going to just consolidate the terms that are real and imaginary between these two. So basically, I noticed that there is a cosine 3t here and a cosine 3t here. There's a C1 and a C2. So I'll do this in one step. I'll just say that basically there's a C1 plus C2 times cosine of 3t plus there's a C1 I sine of 3t and a C2 negative I sine of 3t. So I'll just pull out a neg I from both of those. This first one has a C1, this one's a minus C2, and then there's a sine 3t. So I'm just consolidating the real and imaginary parts from each of those two pieces. But the C1 and C2 are arbitrary constants. So if you have two arbitrary constants that are added together, that you could just define as a new arbitrary constant. And I'll just say this is, let's like define this as C1, a new C1. This whole thing that's multiplied the sign, I'm going to include the I as well and just call I times C1 minus C2, this whole thing as a new arbitrary constant C2. So here, the assumption is that C1 and C2 may be a complex. They're arbitrary constants, and they could be complex in general. And if we say that, then we can just say, okay, well, this whole thing that's got I multiplied to it is just a new constant, C2. Then we're left with C1 plus times cosine of 3t plus C2 sine of 3t, which has no, well, it doesn't look like it has any complex. It's not, nothing is imaginary now. It's all real now. Yes. The purple, so there's a plus here. Then we wrote this green purple box as this, and that only changed a bit because cosine's an even function, so it became this, but there's a negative here. And then that negative here is here, because I have a distribute the C1 to this and distribute the C1 to this, and then that showed up here. And I'm saying this whole, and then there's, so because this negative showed up here, I'm leaving this as a plus here. And then I'm saying this whole thing has to be a new, well, I'm just redefining it as a new arbitrary constant C2. And so does that help? And then this one right here is the same thing as this right here. So this green underline and this green underline are the same thing. Where you can say C1 and C2 are arbitrary constants, C1 and C, well, these C1s and C2s are slightly different because it's like redefining these, so they're not exactly the same, but we're just redefining because they're arbitrary constants. So up to an arbitrary constant multiplied to each of these two terms, they're the same. And you know, so this though looks like it's a real now because there's no more i's here. I mean, in reality, the I is hidden in the C2. So the C2 did have an I in it, but you have control in making, like, now we have our hands on a general real solutions. What's the general real solution? We can basically use this with C1 and C2 is real. So we can easily keep real by choosing C1 and C2 element of real numbers. So these symbols are, this means complex and this means real numbers. So you can take this and easily keep it, like if you're only interested in the real solutions, then you can easily do that by just saying, I want this, but with C1 and C2 reals. If you want complex solutions, then yeah, you can have C1 and C2 be complex as well. But if you want to just look at the real solution, then you can easily do that with this one by just saying it's this with C1 and C2s all real only. Then you're looking at just the subset of solutions that are real. And in practice, that's for at least our class, when we apply this to spring mass systems, vibrations, and electrical circuits, will be only interested in the real solutions. And you may be given initial conditions that are also real. And if you had initial conditions that are real and you use this complex version, then your C1 and C2s will also be complex. Whereas if you use this version, then if you have real initial conditions, then your C1 and C2 be real, and you're just staying real the whole time, and you don't have eyes flying around everywhere. We'll do an example where that'll become apparent. And so we would generally be interested in this form of the solution, which uses Euler's formula to take what we know from before. What we know from before is that whatever root we get, one of them is e raised to one of the roots times t plus e raised to the other root times t. This is consistent with what we saw like up here, right? When we got two roots, 2 and 1, one of them is this and one of them is this. If they happen to be complex, you could still do the same thing. But if you wanted to just get your hands on the real solutions, then you can extract the real and imaginary parts using Euler's formula, and then redefine constants where one of the constants will be complex, but you can easily force this to always be real. Then you can just choose C1, C2s that are real. So Euler's formula here is e to the I theta is equal to cosine of theta plus I sine of theta. Have a variety of ways to show that to prove this or verify this theorem or this formula. One way that is common is if you just do Taylor expansion. So E of t, if you Taylor expand, looks like this. So if you now just replace t as I theta, right? Because you see from here. So this t now is I theta. That means every single t that you see in the Taylor expansion is I theta. So this t becomes I theta. T squared becomes I theta squared, but I theta squared is like I squared theta squared, but I squared is negative, so that's why there's a negative here. And then cubed is going to have another factor of I that shows up. And then, so that's the Taylor expansion for E of I theta using the Taylor expansion of E raised to the t. And then you can try to take terms like, so instance, this term is 1, and then you have this term, and then this term, and I'm just going to write those here, and write those here, and write those here. And then you can do the red terms, which are this one and this one. There's more because they go infinitely further. But it turns out that this expansion is the same as, this is the Taylor expansion for cosine of theta. And then this right here is the Taylor expansion for sine theta. All I did with this up here is all the green ones are the real terms in the Taylor expansion, and all the red terms are the imaginary. They have eyes. That's why there's a factor of I out here, because I'm just saying theta has an I on it, and then this one is I theta cubed over 3 factorial has an I on it. And so if all these terms are the Taylor expansion of cosine and all these terms are Taylor expansion of sine, then that means that you have that this is equal to cosine theta times a plus I sine theta. That's just if you wanted to see where, if you wanted to justify where the Euler's formula comes from. Let's do another problem that uses complex roots. So if you took this and wrote the characteristic equation, it'd be r squared minus 4r plus 13 is equal to 0. And you, in this case, really might find it easier to just use the quadratic formula rather than try to factor. So you'll have negative. So this is it. This is the quadratic formula, plus or minus the square root of, you take the 4 and square it. So it's negative 4 and square it. So 16 minus 4 times the a times the c is 13. And then you're going to divide this whole thing by 2. If you do that, then your roots are going to be 4 plus or minus, the inside of the square root is going to be negative 36 over 2, which means you have 4 plus or minus, so I'll just say that the 4 and the 2 will go away, and you got 2. And then you have in here the square root of 36 is 6, but because it's negative, it's I, and then there's a 2. So this is 2 plus or minus 3i. Those are the complex roots. They'll always occur in conjugate pairs because of the fact that there's a plus or minus here. So there's 2 complex roots, but what's different about this one compared to the previous one is that previously we had that it was r is equal to plus or minus 3i. It all was pure imaginary. but now we have a real part. So we have like a 2, which is the real part. And that changes it a little bit, but not dramatically, but it does give you an extra factor. So when you write the complex solution to this, it'll be C1 e to the 2 plus 3i times t. Because you take the first root, and then plus C2 e to the 2 minus 3i times t. So that's the complex solution. And of course, we were interested in the real solution, so I'll just put this here, and then this is technically correct, but if we're all interested in the general real solution, then we want to use Euler's formula. So before I use Euler's formula, what I'll say here is that this this quantity, this thing right here is like it's like e raised to the, if you distribute the t to each of these, it'd be e raised to 2t plus 3it. Okay, distributing the t to each of these, and then if you have an exponential that's multiplied by well, you have an exponential that's raised by two things that are added together. We've seen this before, but you could split this into a product of two exponentials. So you could do this. So this I guess I should write this whole exponential here can be written as this, but then it splits. And so using that, you know that this is the same as C1 times this. Plus C2. Similar idea with this. The only change is going to be you'll have e to the 2t times e to the negative 3it. So same idea that you will get with this one. It's just a negative there. So you can rewrite these like this. And there is something that's common in both of these, is this one. The e to the 2t is common between these two, so you can factor that out. So you get e to the 2t times c1 e to the 3it plus c2 e to the negative 3it. And what did we notice from before what this was? So we actually saw this one already, because this is just, I'll copy it, is just paste it. So we see that's what I'm just grabbing that from that below. But if you look at this is exactly the same as this, right? C1 e to the 3it, C2 e to the negative 3it, C1 e to the 3. They're the same. And so we found that this was equal to this thing right here. So we're not going to go through all this again, because we saw that this quantity here, this complex exponential expression, was, after all this work, equal to this if you wanted to use Euler's formula. So we'll just copy and paste that right here and say that this is just equal to this from before. So that means that our work is pretty much done. We are just going to have that this is just equal to 2 e to the 2t times this thing. And we are, I mean, I guess the only thing I could do is just write it out like this and say it's going to be the same as C1. I'll just distribute this out. So C1 e to the 2t cosine of 3t plus C2 e to the 2t times sine of 3t. And that is actually the solution to this, the real solution. So if you wanted to just look at the real solutions, this you can easily make sure is real by choosing C1 and C2 that are real. And I'm going to now point out some So there's something nice about this is there's a pattern here. If you look at this, let's say you have, okay, I'll just write this and say, you have some root, right? You have complex roots. Complex roots will always occur in conjugate pairs. So you have R is equal to some real part, alpha, plus some imaginary part, beta. And so your roots will always be like alpha plus I beta. Now, if you have your complex roots like this, then your, and it'll be plus or minus because it's always going to be in conjugate pairs. If you have a root that's like this, then you'll always get that this is the same, this will always give you a solution. So let's see where things ended up falling. So here, what's our alpha in this one? 2 is our alpha. And our beta is 3. It's the real and imaginary parts. So this is our alpha. This is our alpha. And then this is our beta. So in general, your solution will always be like this: C1 e to the alpha t cosine of beta t plus C2 e to the alpha t sine of beta t. And they're all just going in this spot. So this is your alpha is here, your alpha is here, and then your beta is here, your beta is here. And you're just reading off. So this is our beta here, and this is our alpha here. This is the punchline. So in the end, you'll always have this be true from all the work that we went through here. And so anytime you have a complex root, you look at the real and imaginary parts, and then you just put it in these spots. Okay. So this is the general formula for the complex general real solution for complex roots to the characteristic equation. So you don't have to do all the Euler's formula. You look at that to appreciate where this comes from. But in the end, this is what you're going to use. So you'll have your differential equation, constant coefficient, homogeneous. And if your complex roots are has real alpha and an imaginary beta, those real alphas will go here, and beta is imaginary, and those will go in here. And of course, in our class, you can bring a formula sheet, whatever. So you just write this on your formula sheet, and then you just use it. You don't have to derive this from scratch using Euler's formula from complex exponentials. But it's good to understand where it came from. Like all this work that we did is where this final expression comes from. If you wanted just the real part, or the real solutions. So why is the real solution useful is if you have a differential equation that has real initial conditions, then it's going to be a pain to use the complex version because your C1 and C2 will also be complex in that case. So you want to keep everything real, then you want to also start with just a real general solution. So for this one, if you were to write the characteristic equation, it would just be R squared plus 2R plus 2 is equal to 0. And you're going to just use the quadratic formula probably because it's going to be imaginary roots. So you're going to have R is equal to -2 plus or minus the square root of 4, because 2 squared, minus 4 times 1 times 2, all over 2. And so then this will be -1 because -2 divided by 2. 4 minus 8 is -4. Square root of -4 is 2i divided by 2, so it's plus or minus I. And we see immediately that our alpha is 1. So I'll just say here alpha is 1, or -1, sorry. And our beta, which is the imaginary part, is equal to 1. So you can use the what did we got before? So we'll just use this giant thing that we saw before. So what does this tell us? This tells us that if you have alpha is equal to -1 and beta is equal to +1, then your solution must have been C1 e to the t, because it's gonna, or negative t, because your alpha is -1. And then you'll have cosine of t, because beta is just 1, plus C2 e to the negative t, sine of t. So this is your general solution. And you're interested in using these initial conditions. So if you're going to use these initial conditions, then you have two of them. You have one of them is x of 0 is equal to 2, and the other one is going to be this other one, but we'll just do the first one first. So when you have x of 0 is equal to 2, and this is your actual solution, then you'll say 2 is equal to C1 e raised to the 0. E raised to 0 is 1, so I'm not going to write that. Cosine of 0 is also 1, so it's just this. This second term goes away because it's sine of 0. That's going to go away, so that's all we have. This is equal to this. Now, the other condition, the other initial condition is on the derivative. This requires us computing the derivative, which is a little bit of a pain. So I'll need space to just compute the derivative on this one. Maybe just so that I can save myself from doing two product rules, I'll just combine this into, so I'll just say that this is the same as e raised to negative t times C1 cosine of t plus C2 sine of t, because they have e to the t, that's common. And then if I took the product rule on, or take the derivative of this, then you'll just have x prime of t is equal to, you use this expression. I take the derivative of the first, which is going to be negative e to the negative t, times I copy all of this. And then I say plus, I copy the first times the derivative of the second, which is going to be negative C1 sine of t plus C2 cosine of t. That's the derivative. And I have to apply this condition. So it's like saying I need to put in x prime of 0 is equal to 1. That's our derivative condition. What does this give us? This gives us that x prime is equal to 1 whenever all your t's are equal to 0. So imagine this t being a 0, 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 0, and 0. And let's just see what that gives us. First of all, e raised to the 0 is just 1. This whole thing, only the sine of 0 is 0, so we're just left with C1 from this whole expression here. Now this one, e raised to 0 is also 1. Sine of 0 is 0, so all that's we were left with here is C2. So you see, all the zeros plugged in will just make this thing equal to just C1 plus C2. Or negative C1, sorry. There's a negative sign here. This negative sign. There's a negative e to the negative t, but this e raised to the 0 is 1, but there's still a negative right there. So I'll just make clear that we have a negative here. And you'll have the C1 from before is 2. So this is equal to 2. So we're left with 1 is equal to negative 2 plus C2, which means that C2 is equal to 3. And so our final solution, I'll just copy and paste. This we had was our general solution, but now we found that C1 and C2s are 2 from the first condition and 3 from using the derivative condition in combination with the other initial. So this is the solution. If you ended up using the complex exponential, which is like going to be the solution that looks like this right here, where it's 6c1 e to the something that's complex times t times c2, then your c1 and c2s will have to be imaginary. it's a little bit more work, because what's going on is you're gonna say, well, I need to, set this equal to, well, I guess it might not be that bad, because then you'll just get this is all zeros. But this is what you'll get for this problem, where you have the solution, general solution is this, and then you plug in these two initial conditions and get your C1 and C2s. And that's it so we looked at characteristic equation, but 3 cases: distinct real roots, you have repeated real roots, and you have complex. And so that's all the cases that would be possible with the quadratic equation. So that's it for homogeneous solutions for second order. You'll see that it's actually a little more work than first order, right? First order, you just read the left-hand side and just wrote C e to the negative whatever's in front of the x, and that was it. So the second order is harder because you have the characteristic, you have, maybe different kinds of roots, and then you have to use either the form of a solution that's e raised to the like this, e raised to the r1 times t, e raised to the r2 times t. If it's repeated, then one of them is e raised to the rt, but the other one's t e raised to the rt. And then for complex, you have this weird expression. So there's a little bit more difficulty for doing homogeneous second order. Now let's make it non-homogeneous. So now we're going to have a right-hand side that's not 0. So you have here, I'll just say that this is a polynomial input or forcing. But we're going to keep the coefficients in front of all the x's and x prime and x double prime still constant. Eventually, we'll make those non-constant as well. But we're going to keep those constant. And because those are constant, we've seen this before for first order equations, the method of undetermined coefficients was possible. And the idea is still the same. You try to propose a solution form for the particular solution that would give us hope for making the left-hand side resemble the right-hand side. And if you have a 2t plus 5, we saw this before, we usually thought of it as the same degree polynomial. So this is a first degree 1 polynomial. Degree 1 polynomial. Then you'd think it's going to be a general degree 1 polynomial as well. Why does this make sense? Is because if you plug in this into the x double prime, it will end up actually completely going away, because it'll just be taking the derivative of this once will give you a1, and then taking the derivative of it again will give you 0. So the x double prime term will be 0. If you plug this into the x prime term, you'll have just a1. If you plug this into the x term, you'll have all of it. You'll have a naught plus a1t. So in general, your left-hand side will have a bunch of terms that are like constants, in addition to a term that's got a t in it because of the fact that you're plugging it into this x, and that one's the only one that's going to have a term that's t. But that's okay, because the right-hand side has constants and a t. And so you definitely do not want to plug in, like we mentioned before, you don't want to just plug in a constant a. Just plugged in a constant a, then of course x double prime will be 0, x prime will also be 0, and x will be a, but you'll have no t terms on the left-hand side. And there's no way you're going to get the left-hand side to match with the right-hand side if you plug this one in. You could go higher and plug in something like a naught plus a1t plus a2t squared. If you did that, then the x double prime term will end up being probably a term that's constant, because the squared would come down and then it'll come down again. This one will have a linear term, but the x will have a quadratic term. Yes.
The right-hand side column will be able to
Yeah, you want it. You have then you'll use this. You'll use this one where you have the a2t squared. You can always go higher in your particular solution. You can go higher degree, but if you did the matching terms on each side, you're going to notice that there's t squared terms on the left-hand side where there's no t squared terms on the right-hand side. So you'll automatically find that you'll have to make this equal to 0 in order for, you just force this to satisfy it. So if it's gonna be 0 anyways, why even put it in there? Just start with this immediately. So that's why technically this isn't wrong, but it's gonna be unnecessary because you're just gonna find that through the whole algebra, you'll have found that A2 must have been 0 in order to get the left and the right-hand sides to match. Then if this was going to be 0, then why do we even include that term? We could just leave that out and just have these first two terms. So we'll do that. So it's not, this is like almost no difference from what we saw for first order. Only difference is that now we're still plugging it in, but there's an x double prime. So you just take this and take second derivative of it and plug it into this term. But all the other things are the same. And then you're just going to match your t terms and your constant terms, and then find your A0 and A1, and that's it. And so it's like not that bad, actually. Second order is actually not really that bad, because you just kind of do the same thing, but it just has the x double prime term. I have office hours in this room, so if you wanted to stay, we can stay and I can give you problems to do for the test. Yeah.
Have a great weekend.
Have a good weekend.
Yeah, let's go back.